In this lecture, I want to talk about selection sort, and I'm going to do it using some slides from the textbook. We'll start off with a simple example. We've got a bunch of cards and we want to sort them. So how are we going to do this? Well, we find the minimum element, that's 2 in this case, and we're going to swap it with I. That's the number of things I've already sorted. So at the beginning, I is 0 because I haven't sorted anything. And we're now going to swap min and I. And now I've got one thing that's sorted. It's in its final place. So we can increment I and look for the next min. So note that we're looking for the min from I up to the end. And in this case, that'll be 3. We can then swap and now increment. We've found one more element in its final order. We can keep proceeding like this, and eventually the whole array will get into the right position. You can think about this like going through a bunch of papers, and you find the paper that you want at the front and then put it to the front, and you just keep going, finding the next one, the next one, the next one, and putting them into their final order. And eventually you end up with something that's sorted. So to understand the correctness of this algorithm, we need to understand the invariant that it maintains. So what's the invariant as we go along? Well, the first items from 0 up to I are already sorted. They're already in their final order. And therefore, as I gets one bigger every time, I'm increasing that up to the final size. And once I've tripped off to n plus 1, or once I'm off past the end of the array, that means that every element in the array is sorted. We are also maintaining the invariant that once we've got an item I here, there won't be anything smaller than it to its right. There may be something equal, but there won't be anything smaller. Note that this algorithm may actually swap things that are equal depending upon exactly how it's encoded. So it's not necessarily a stable algorithm, but it is correct in the sense that I will end up with an array that's completely sorted. So how do you code this? It's not difficult. We need to have code that is going to move the pointer forward. We're going to have code that finds the minimum entry. So that's not difficult. We just need to start at I plus 1 going up to n and compare the jth element with the min that we have found so far. So we're looking for the min so far through this array. And what I'm going to store here is not the value of the minimum, but its position. Because eventually, once I find that minimum element, I want to swap it. And in order to do the swap, I need to know the position of that min, not just its value. I don't want to just write the value into I. I want to swap the value that's currently in I over to the min as well. And so we're going to use an exchange method that does this exchange for us. These auxiliary methods, less and exchange, are implemented in the textbook to do the following. So the less method just takes two comparable things and compares them. This is using the natural order for the comparison. And in the actual coding, there's a variant that uses a comparator if you should provide one. The exchange method simply swaps two elements in an array. It's a pretty standard algorithm. I take the ith element and store it in a temporary, then I overwrite the ith element, and then I copy the temporary back into the jth element. Once you've got the auxiliary methods, the sorting algorithm is pretty straightforward here. So to sort the array A, I'm going to simply go for I equals 0 up to its length. And within that, I will look for the minimum. So here's a look for the minimum algorithm. And once I've found that minimum, I'll do the exchange, then increment I. If you look at the code in Eclipse, you'll see that I've provided a main method for you, which does a sorting of a simple example. So this is just sorting some letters and printing out the sorted array. And then I'm going to run some tests for complexity. I got tired of writing doubling tests over and over again, so I wrote a simple little class which does some stuff. The run method that I've written takes several parameters. The first one says what in should be to start. The second one says how many times to repeat the test. And the third one actually takes a number and generates some data for you. So here I'm going to take a number in, whatever's passed into me, and actually generate an array of random unique numbers. And finally, we have to say what to do during the test. So what's the thing we're testing? And what I'm going to test here is the sorting algorithm. So don't get too caught up on the exact coding of this. I'm using some function notation to pass functions around. But the basic thing here is we're doing a test to check random unique elements in an array and what kind of performance I'm getting. To get milliseconds and stuff, it's straightforward. I also wanted to get some more accurate numbers, and so I've instrumented the code here with some conditionals to increment and count the number of operators that we're performing. And you can see what I'm counting here is the number of comparisons and the number of exchanges. And it's quite clear that it's pretty stable here. So regardless of what kind of input I'm giving, so here I have a random unique input. Here I have a random input, but it's only two values. So this is just like 0 and 1 alternating. And here's a partially sorted array. So this is something that's pretty much already sorted, but not quite. In any case, it doesn't matter because selection sort is dominated by the comparisons. In fact, you can see there's a little variation here, like we get 2 million here and we get 199,000 there or something like this. That's really having to do with how many swaps there are. So if we stop counting the swaps or the exchanges, then you'll see that really the number of comparisons is dominating here. And the number of comparisons is always exactly the same, regardless of the input. So no matter how many times you run this, even with random data, always exactly the same number of comparisons. And this makes sense because we're going through the array from 0 to n, then 1 to n, then 2 to n, then 3 to n, then 4 to n, etc. What we have there is a triangle, half of a square, and indeed we're getting quadratic performance. If you look at just the exchange operations, instead of looking at the comparison operations, you do get data dependencies here. So the number of comparisons I'm doing is going to depend on the input. In fact, you can see it's much lower for things that are almost sorted. And that makes sense. If your array is almost sorted, you don't have to do as many swaps. And that'll be consistent as long as the array is almost sorted. I'll get small variances in the numbers, but they won't be that high. So we don't have a huge amount of swaps here. What we've got is a huge amount of comparisons. So comparisons are dominating this number and resulting in quadratic performance regardless of the input array. The mathematical analysis reflects the experimental results we've seen, and so we will actually get quadratic performance. In this case, we expect about n squared over 2 comparisons. And that's data independent. And the number of exchanges depends on the data, but the worst case is in exchanges. There's a lot of ways to visualize sorting algorithms, and people love to do this online. So this is one visualization that you can see. I've put a link to several kinds of visualizers in the course notes or the notes for this lecture. Here's the one that the textbook actually uses. It's got visualizations for all sorts of sorting algorithms here, and you can just watch them in action. It's somewhat hypnotic. If you have a favorite sorting algorithm, you can drill in and look at it. And you can also look at different kinds of data sets. So what we're looking at here is completely random data, nearly sorted data, so it's almost sorted but not quite. Reversed data, which is often a bad case for some algorithms, and something with few unique elements. So that's a lot of repetition, which is handled by my last test. If you just drill into selection sort, you'll see that the performance of the algorithm really has nothing to do with the number of swaps. It's completely dominated by the number of comparisons. There are lots of interesting ways to visualize algorithms. One of my favorites is actually to use sound. Here's the sound of sorting. This is selection sort sorting. So that was selection sort. Let's play that one more time. And you can sort of hear the pitch corresponding to the number of the comparison. Yay, selection sort. The other links I've included here are more general. They're not just about visualizing sorting algorithms, but visualizing all sorts of different algorithms. And some of these are really interesting. So this is one from the University of San Francisco. There's some other ones here from, for example, the Open Data Structures and Algorithms project, where they have some interactive visualizations that might be useful. Oh, look, a heap. Because JavaScript is the language of the web, there's really some great tools also for looking at algorithms using JavaScript code to both code the algorithm and then also to step through the visualizer. People have come up with all sorts of goofy ways to visualize sorting algorithms. For example, a gypsy folk dance. Here, the first 5 elements of the array are already sorted, and you can see the comparison operation happening by this sort of pair dancing that's going on during the gypsy dance. So the champion there, 5, has won this round, and she'll go to AF5. Now we have the gypsy dance competition for the next minimum, and so on and so forth. This is what I do on the weekend, by the way. We mostly just have this kind of gypsy folk dance for sorting algorithms around the house.